Driving in heavy traffic is hard work. The driver needs to concentrate at all times, respond quickly to new situations by braking and accelerating, and even a single mistake can be fatal. How about a solution that not only shows safety but also reduces harmful emissions and increases fuel efficiency? We have a solution, and we present to you the adaptive cruise control. ACC can take the pressure off the driver during journey by adapting to the flow of traffic. But how does it work? The driver selects the speed and the distance to be maintained from the vehicle ahead. A long-range sensor detects the driving situation ahead of the car, and based on this data, ACC can calculate the distance, direction, and relative speed of the car ahead. If the car detects another car ahead of it that is traveling at a slower speed, our car will also slow down and maintain a selected interval behind the car. And as soon as the road gets clear, the car can finally speed up again. We had to use a toy car for our project, but the model is basically a prototype of an actual car. Let's talk about the implementation. The components that were used in the project are Raspberry Pi, motor driver IC, ATmega 328P, ultrasonic sensor, and RPM sensor, all this mounted on a toy car. Let's discuss them one by one. First up, we have Raspberry Pi. We use Raspberry Pi as the central unit or control unit. It acts as the brain of our project, and each sensor and actuators interface directly or indirectly to it. Secondly, we have motors and their driver ICs. In our model, we have used 4 motors for 4 wheels, so we had to use 2 motor driver ICs per side. We set the reference voltage as 9 volt to get high speed, as it helps us achieve better results. We use ultrasonic sensors to detect any obstacle and thus measuring distance from leading car. We use this information to decide whether to accelerate or apply brakes. Trigger 8 bursts of directed 40 kHz ultrasonic waves are transmitted by a transmitter, and receiver waits for waves to come back after striking the obstacle, and thus jotting down the time required for an entire journey. From this time, we can calculate distance by using the second equation of motion. Although for rear cars, we'll have to use radar, lidar, or camera for better accuracy. We can use speed sensors in order to ensure that the car is complying with desired speed as dictated by the control unit. We make use of LM319 comparator along with the FC03 encoder. RPM sensor gives 2 outputs. One is digital, just 0 and 1, and second is analog, values ranging from 0 to 1023. So as a result, we have 1024 different voltage levels. We can decode these voltage levels using an ADC. Surprisingly, there is no ADC in Pi, so we have to use an external one. For higher computation power and fast response time, we use ATmega 328P. Interfacing of RPM sensor with Pi and ATmega has 2 main steps. First of all, converting analog signal into a digital one using ATmega, and then communicating these signals from ATmega to Pi. Thus, we have 2 parameters, one is distance and second is RPM, that serve as inputs of PID controller, upon basis of which we can integrate our system. To sum it up, we now have a continuous process via which we will be sending speed profiles of both the current car and the leading car to microprocessor, and then monitor and dictate changes that occur as a result. The graphs depict how the speed of leading car will be followed by that of the following car. Our toy car will look something like this. So let's talk about where would we have been if we had proper access to other facilities. The answer is the Cooperative Adaptive Cruise Control, or CACC. It's basically an advanced form of ACC that works upon the same concept of platooning, but it further reduces air drag and helps us achieve improved results. So rather than only communicating between adjacent cars, we now consider them as a group. It all boils down to this final question: why do we even need to do this project? The impacts and benefits of this project are increased safety, relaxed journey, increased fuel efficiency, reduced emission, reduced congestion, longer road life, and faster braking. At the end, we would like to thank our advisor, co-advisor, and the staff of NURS for their help. Thank you.